Sam's like, you're on time. What are the odds? About 8 to 1. About 8 to 1. Let's see, we'll begin with a word of prayer. Dear Father, we thank you for this morning. Thank you again for these students. Just ask you to bless this day, bless our work today, that we would glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. So, you guys haven't done that bad on anything, but still I'm going to make you listen to this. Let's see here. So very wrong. I don't think they had talking picture shows in France in 1820. Ecole Polytechnic.
English guy, like McKinley says, don't rain truer than this hair store I'm about to unfold happened back in ancient France.
Ancient France. There are small parts of that which are accurate. Actually, I don't know. See, I've heard different. Mostly, I've just heard that he died over a duel that was political in nature. I don't know if it involved a woman or not, but the idea that it was about a woman named Stephanie is just kind of fun. But I feel like there's a high probability that Stephanie was the name of one of their girlfriends. So.
Yeah.
Yeah, I just wrote a paper on it.
Oh, tell me more.
I think that he fell for the Stephanie girl, and then she basically.
Oh, so this is actually accurate.
No, yeah.
Oh, wow.
So they found like on some of his work on the back where they think he like got a letter from her, and then he tore it up, and then he was trying to like remember what she wrote, and so he was like writing it out, and she basically told him, "I just want to be friends." And then a few months later, she sent him another letter and said, "I don't even want to be friends." So she kind of just dumped him.
So she dumped him. Why did that make him get in a duel?
No, it wasn't. I don't think the duel was.
The duel was unrelated.
Oh,
Yeah.
oh, okay.
I think it was just political.
Okay, so the claim that because I think the song would indicate that these are connected events.
Yeah, I
Yeah,
don't
yeah.
think they're connected,
I didn't
but
know the song. I didn't hear all the lyrics.
Well, yeah, maybe we can debate the validity of this piece of mathematical comedy, but I do enjoy the slightly atemporal juxtaposition of the old American West and ancient France.
Yeah, well,
Yeah, Galois. It's good stuff. All right, so we are in the section 14.6, the Galois group of polynomials. Sorry. 14.6, Galois group. So, let me write down some key points here. So, if we consider a separable polynomial f of x, right? Think about f of x. Separable. What have we learned about such a polynomial? We've learned that we can look at the Galois group of it over some splitting field of f, right? In particular, if we have k as a Galois extension, right? If k over f is Galois extension, what does that entitle us to? Let's see here. What do we have? Well, I mean, I guess if you want to get picky, we have what? The degree of the extension over f is what? The order of the automorphisms of k which fix f, right? And that, in this case, is called the Galois group of k over f, right? Okay, so to each polynomial, then, we associate a group, right? And it's, sometimes you run across correspondences in math which are kind of pretty loose, right? Like, for example, nth order polynomials with real coefficients are associated with Rn plus 1, right? Unless you do some kind of special stuff, Rn plus 1 and polynomials of order n, I mean, that association is pretty much just, it doesn't, unless you do extra things with Rn, it's not really going to encode most of what it means to be a polynomial, right? It's just capturing the fact that polynomials form an n-dimensional vector space. Well, this correspondence between the polynomial and the group, which corresponds to it, is a much more interesting correspondence. There's lots and lots to it, right? It tells us so much about the polynomial. But he says, any automorphism in the man, I cannot talk today. Any automorphism in the Galois group maps an irreducible factor of f of x to another irreducible factor, and the automorphism is uniquely determined by its actions on these roots. So if we label alpha 1, alpha 2, alpha n, the roots of f of x, then what did we learn? What is, if sigma is an element of the Galois group, yeah? Right. And you could justifiably start saying that it's really the Galois group of f of x, right? I think that may have happened in a previous section we skipped already. Yeah. So if sigma is in the Galois group of the polynomial, which is that, all right? I know. I think you actually probably need to state the base field as well to make that meaningful. But okay, anyway, just for the sake of this somewhat loose, well, it's not that loose, but slightly loose discussion. What can you tell me about sigma? What does it do to these roots? What is sigma of alpha 1? What is, if we look at this, sigma of alpha 1, sigma of alpha 2, right? As a set, alpha n, right, is the same thing, right? So, in other words, we can view sigma as a permutation on the roots, right? So another, right, sigma. It fixes everything else. Well, yeah, like you said, it's not quite that, but its action on the roots determines what it does to everything else, because the splitting field can be viewed as f adjoin alpha 1 through alpha n, right? And since f is fixed by an element of the Galois group, an f-fixing automorphism, you're right. What it does to the roots says what it does to everything. So as it permutates, what on earth? Permutates? No. What is this? What's wrong with me? Permutes the roots. Oh, yeah, I was functions. Let's just, there we go. Okay, fixed. Anyway, so there's an obvious injection of the Galois group into the symmetric group of order n, right? And if you think back on it, I more or less showed you guys this idea when we looked at what theorem in 421. Something very similar to this idea anyway. I think it was, is it Cauchy's theorem? Cayley or Cauchy? Cayley?
Oh, yeah.
We look at the right. We look at the action of the group on itself by left multiplication, right?
Yeah.
This is very similar in flavor to that. I mean, it's not quite that, I guess, but.
What exactly does that curled arrow symbol mean?
Oh, injection.
Oh.
It means there's an injection of that into that. Excuse me. So he says it's clearly a homomorphism. Both group operations are composition. And so we can think of the Galois groups as subgroups of symmetric groups, all right? And furthermore, since the degree of the splitting field is the same as the order of the Galois group by the fundamental theorem, this explains from the group theoretic side why the splitting field of a polynomial degree n is at most what? Right. So basically there's let me give it a name, psi. Okay, so psi of the Galois group of k over f is a subgroup of Sn, actually, right? And so the order of this is less than or equal to order of that, and the order of that, of course, is n factorial.
And we didn't already use this back in building up the Galois correspondence machinery.
No, I don't think so. Those. Yeah, as far as I don't remember in my reading seeing any kind of like nuts and bolts of symmetric group used to build things up. I think it's all been very map theoretic arguments. You know, I mean, I'm sure you could go back and look at those and see the symmetric group in there if you looked at it with symmetric group colored glasses. You know.
Right. I guess I meant.
I mean, there are people who go back and look at Newton's Principia and say that you can see algebraic topology in it.
Right. I guess I meant more like the fact that we derived earlier that the splitting field has to be at most degree n factorial. Do we use that fact?
No, there I think what we used was just the, so we pick one irreducible factor, pick one irreducible factor of the given polynomial, we quotient by that.
Right.
That gives us a degree, an extension by degree at most, the degree of that.
Right.
If we quotient by a linear factor, do we ever do that? I don't know, but if you could, it's foreign to my experience to quotient by a linear factor, right? Like, it seems like we almost always quotient by conjugate, like quadratics, because I mean, such examples exist, but they're a little bit more foreign to our experience for the most part.
I guess what I was saying is, because in the stuff through like 14.2, we use, or we derive that being a Galois group, or being a Galois extension is the same as being splitting field of a separable polynomial.
Mm-hmm.
So, but I guess then we didn't argue because that factorial privilege.
Right. Yeah, we had a direct, just extending, keeping track of the degrees of the extensions as they unfold, I think from successive. Anyway, so, and he says, more than this, if you have a factorization of f of x into irreducibles, f1 through fk, where fi has degree n sub I, then since the Galois groups permutes the roots of irreducible factors amongst themselves, right? So he even points out that, you know, if we have f of x is equal to f sub I of x, I mean f1, f2, fk of x, where these are distinct, irreducible. Well, I guess they don't have to be distinct irreducibles. They could be, oh, wait a minute, we assume separable. Okay, so they're distinct irreducibles, right? Then distinct irreducibles, the roots of these irreducibles in the splitting field, they're what? Right, they're roots of some, if you take a particular root in the splitting field, right, it cannot be the root of more than one of these irreducible factors. Because if it was, that would imply what? We'd have it wouldn't be separable, right? So that then implies that when we think about the Galois group acting on the roots, it's going to keep the roots of the first polynomial inside the roots of the first polynomial, and so forth. Like the roots stay in these little buckets with each irreducible factor and get permuted amongst themselves. So if the degrees of these are n1, n2, nk, then that implies that, you know, the Galois group of this guy would be isomorphic to something like, well, it would be it's a homomorphic image. There's an injective homomorphism of the Galois group of this thing inside Sn1. Oh, sorry, notation. Sn1. We don't want to deal with the n minus 1 sphere, right? Sn2. S and K like that. Yeah. So, understanding this also gives us a lot of insight as to the structure of a Galois group based on the factorization. We can kind of anticipate things. And I suspect working out the test question that none of you guys had time for, that's due Monday, will give you added insight into this whole thought process. Is that fair, Emily? Yeah. I think that's true. Okay, so, and then he gives a couple of examples of that. He says if we look at the biquadratic extension, so if we look at Q adjoin square root of 2, square root of 3 over Q, well, what else? So this is the splitting field of what? You guys remember? X squared minus 2, x squared minus 3. So if we just irreducible, that says that the Galois group has to fit where? Has to be some sort of inside what? S2, right? S2. Of course, S2 is kind of boring, right? S2 is Z2. And as it happens, this injection is actually a surjection because the Klein 4 group is the Galois group of this, as we've worked out before. But he in this, he also shows how to think of it directly as a subgroup of S4. So here's what he says. He says, label the roots, alpha 1. So if you look at like the old, I think if you look at the old works on, Galois theory, you'll see that it's just all about, permutations of roots. This more modern way we've been looking at it comes later. But of course, it makes for certain arguments being much cleaner. Those arguments probably would be supplanted by technical, dirty hand-to-hand combat with permutations in the previous way of thinking, right? Whereas we just like, oh, isomorphism descends, woo! I'm not a math historian, so I don't understand the the prehistory, if you will, of Galois theory that deeply. But so those are your roots, and so we had like sigma of the square root of 2 equals minus square root of 2, right? And sigma of square root of 3 equals square root of 3. So it fixes that. And we had tau of square root of 2 is, I said tau and I wrote sigma. Oh, sad. Square root of 2. Square root of 3 maps to minus square root of 3, like that. So what is it, as a permutation on the roots, what do we have? We have sigma of alpha 1 equals to what? Alpha 2. And we also have sigma of what? Alpha 3 is alpha 3. And by the way, sigma of alpha 4 is also what? Alpha 4. So what does this do? It basically sends 1 to 2, and it fixes what? 3 and 4. So if you wanted to write sigma as a permutation in S4 in cycle notation, it's just the transposition 1, 2. Where we're actually looking at the labels of the roots to come up with the explicit permutations, right? Which is the same, that's what I'm saying, that's the analogy I was making the last semester. That's what we did to come up with this explicit permutations in the finite group. We looked at the labels of the finite group and saw how it shifted, how left multiplication by group elements shifted the labels, and saw that left multiplication corresponded to specific relabeling permuting the labels. And so this one, this does what? This sends, basically this is sending what? 3 to 4, right? And this one is tantamount to sending 1 to 1 and 2 to 2. So tau is the transposition 3, 4. Of course, those are both order 2 and S4. And what happens when you multiply them? What's the order of this permutation? It's 2, right? Least common multiple of 2 and 2, also known as 2. So, good. So you got 3 elements of order 2. It's a group. It has at most, it has to fit inside something of order 4. So the reason I know it has to, now the order 4 does not come from this, obviously. Like that's 20, what's 4 factorials, what, 24? So knowing that it has at most order 4 comes from this comment down here, the fact that it's a product of irreducibles of order 2, which means that it has to be isomorphic to some, it has to be has to fit as some homomorphic, well, in the image of the Galois group has to fit inside here somewhere. Let me just, words.
I would say
Embedded, yes, thank you. Much better. And then he looks at the cube root of 2, I mean x cubed minus 2, right? That guy. And what's its Galois group? What is it? Its Galois group permutes what? You got the cube root of 2, right? You have rho times the cube root of 2. And you got rho squared times the cube root of 2, right? So you have those 3 roots, and let's see here. He says basically the sigma, the sigma and tau we looked at before, sigma amounts to 1, 2, 3, and tau amounts to 1, 2, 3. And you may recall from last semester that those two, that 3 cycle and 2 cycle generate S3. Right? So indeed, I mean, we know this. The Galois group of x cubed minus 2 was S3. Up to isomorphism, of course. I mean, technically, it's not S3, right? If we view S3 as permutations on the numbers 1 through 3, literally, right? The Galois group is technically a set of 6 automorphisms, right, on the splitting field of x cubed minus 2, which of course is a particular subfield of C, right? All right, and then so this example is kind of like pathological in some sense. It's like maximally bad. It's as bad as it gets because the Galois group here actually is Sn for this nth order irreducible, right? So, I mean, to my taste, polynomials are kind of nicer when they factor, right? And you don't actually reach the full symmetric group of order n for your Galois group, like in this example. But if we want to study a generic polynomial and just try to, because like, we can work examples one at a time, but it's nice to try to just like take a step back and say, what does Galois theory look like for an arbitrary polynomial of order n, right? And that's what the rest of the section is basically devoted to. At least the next part of the section is devoted to studying an arbitrary polynomial. And here's how you do it. It's kind of sneaky. Definition. This is the general polynomial of degree n. Looks like this. It's x minus x1 times x minus x2 so forth and so on, times x minus xn, where, is the polynomial. All right, whose roots are the indeterminates x1, x2, da da da, xn. You're like, that doesn't exist. To those of you who would say it doesn't exist, can you guys tell me where its home is? If I want two indeterminates, right, what do? I study f of x of y, right? This is naturally identified as, all of a sudden my field has a double bar for the first time. Woo! Fix that, all right. So you can look at this as that, right? And you keep doing this, right? It's the extension of the extension of the extension of the extension. And so likewise, I mean, you can view this as an element of, well, pick your field that you're looking at. Pick any field, I suppose. I mean, I don't know if that really contributes anything. I'm just pointing out it's not, it is something we can look at. All right. Now, it turns out, to understand these, we must understand the so-called elementary symmetric functions. What are those? Have I ever talked to you guys about those before? I don't think so. I might have had a homework problem on them somewhere. Elementary symmetric functions. So we let x1 through xn be indeterminates. And I think it's fair to say that we think of indeterminates in this context as being commuting indeterminates. Like x2 times x1 would be x1 times x2, right? So the first symmetric function, S1, is what? It's just x1 plus x2 plus xn, right? What's S2? Sum of xi times xj. I less than j, xi, xj. Is that right? Let's see, if you're right, we'd have x1, x2 plus x1, x3, da-da-da, plus x1, xn, right? Plus x2, x3 plus x2, x4, da-da-da, plus x2, xn, right? And so forth and so on until we get to xn minus 1, xn, right? Cool, you're right. That is what he has, but, well, as much typesetting as he can afford in the definition in the textbook of this width. I have indulged in a few more terms. All right, so write small. And finally, what's the elementary symmetric function of what's Sn? Not big Sn, but little sn here. x1, x2, xn, just the product of them. All right? Don't believe?
No, it just feels like wedge products.
Oh, it feels like wedge products? That's a good feeling. No joke, Sam. That is actually a very insightful comment. there are horrible homework problems I can show you that I found in Paul Rentland's manifolds and tensors for, I forget for what crowd, for physicists and mathematicians both. Like, I mean, I forget, I can't remember the name of the book, but Rentland's manifolds. He's both a physicist and a mathematician. He's written this like about 150-page, very concise, but very computational in some sense, book on how to calculate manifolds. And one of the reasons I bought it and used it for advanced calculus, like not this last time, but the time before, was because the homework sets in it were just beautiful. And one of the things that he had was this, if I remember right, he has a set of, one of his homeworks involves finding formulas for the determinant that, involves this. I mean, symmetric functions can be found in lots of places. There are quite nasty formulas for the determinant involving polynomials in the trace of the matrix. You guys know for the 2 by 2 case, the trace and the determinant are very closely linked to the eigenvalues, right? Like the product of the for a 2 by 2 matrix, we got what? X minus lambda 1, x minus lambda 2. Suppose it's got eigenvalues, right? If that's the characteristic polynomial, you multiply that out, you got what? X squared minus lambda 1 plus lambda 2, right? X, right? Plus lambda 1, lambda 2. Oh, I'm glad you said that, because it's brought something out here. This is the characteristic polynomial, right? So matrix A with X. Supposing that A has eigenvalues, lambda 1 and lambda 2. So what you may remember, this is the determinant of what? Xi minus A. That's not how I usually do it, but it's the way we should do it. You guys don't make sign errors, so now I have the luxury of making my characteristic polynomial monic all of a sudden. Right? It's been minus 1 to the n times x to the n, the leading coefficient, up till this point in my jibber jabber to you. But yeah, you're big boys and girls, so girl, sorry. I'm not trying to state your plurality.
Thank you.
I mean, I guess. That's a good question for the modern feminist. Would you rather be viewed as a woman or a woman's? I don't know. I don't know the answer to this question. You're like, how about just stop being an idiot? I'll also allow that. But anyway, the point here, if I can actually get to one, is that that's the determinant of A, right? And what's the sum of the eigenvalues for a matrix? The sum of the eigenvalues is the trace, right? But that's really, I'm so happy about your comment, Sam, because you can also see that these are the symmetric functions, right? If we think of lambda 1 and lambda 2 instead of, think of them as indeterminates, right? This is S1, and this is S2.
And then can you extend that?
Oh yeah.
So you just like have x to the n plus s of...
I don't know what to say about the determinant. Generally, that's not on the top of my.
Like the characteristic
Well, yeah, I think so. I think that's like 14.13, which is the next result I was going to share with you guys. Is man, class goes so much better when I leave house at 7. I need to leave the house at 7:40 every day. It's so much better.
Because this is x squared minus s of 2 minus 1 x plus s of 2 minus 2. No. S of minus
I mean, here's the, he says, it's easy to see by induction that the coefficients of the general polynomial of degree n are given by the elementary symmetric functions in the roots. So x minus x1, x minus x2, I think it's better if I write it out rather than say it. This is equal to, well, here's the easy pickings, x to the n, woohoo, minus s1, x to the n minus 1, plus s2, x to the n minus 2,
Yeah, that's what I was getting at.
plus plus minus 1 to the n, sn, yeah. Now we could do that. We could do that induction, but it's probably healthier for me just to do the third order case. I think if I write out the third order case, it'll start to be more believable to you guys. Less severe of a jump here. So x minus x1, x minus x2, x minus x3. We can multiply three things out without too much trouble, right? So we already did so that's like x squared minus x1 plus x2, x plus x1, x2. And you might start to see how the induction goes even from doing this. Yeah? Maybe. So like we can take the first n of them, right? And observe the result. That's the n equals 2 result, right? And then when you multiply this through, what do you get? You get x cubed minus x1 plus x2 x squared plus x1, x2, x minus x squared x3 minus x1. I'm not writing these in a very helpful way, sorry. And then, minus x1, x2, x3. Let me clean that up a bit. So we've got x cubed, goodness, x cubed minus x1 plus x2 plus x3, x squared, right? Because where was that x3 squared? This guy, right? And then what comes next? What comes next? We've got the plus, let's see here, x1, x2, right? Where's my x1, x3? I must have one somewhere here. Ooh, I bet I messed up a sign. Can you tell me where I messed up a sign? The next to last one. Very good. That was supposed to be a plus. Well, and that plus gives me the x1, x3 times x that I was looking for. And then it also gives us a plus x2, x3. X, right? I think that's all the x terms. Yep, and then minus x1, x2, x3, yeah? So there we go. This is your S1. This is S2. And this over here is S3. Now, that notation is a little suboptimal, I think, in this discussion. I mean, if you're going to prove this, I would strongly advise that you say something like, this is S1 of 3. This is S2 of 3. This is S3 of 3, right? As compared to this up here being S1 of 2, right? And here's S2 of 2. Because the total number of indices you're playing with, it matters a lot. And the induction involves the intertwangling of one degree to the next. But yeah. I think I could have a lot of fun going through the gory details of this induction, but I think we should go on. All right? So what's he say here? For any field f, the extension F1 adjoin x1 through xn is a Galois extension of the field S1 to Sn, since it's the splitting field of a general polynomial of degree n. What? What's this S's? Oh, idiot. S's. The symmetric functions, right? So soon I forget. Sad, sad, sad. So his point is this. Again, for any f, any field f, right? The extension f adjoin x1, x2, xn, right? So basically, turn those indeterminates into roots in this explicit field extension, right? He says, well, that is what? He says this is this, all right, is a what? He says it's the Galois extension of what? Keep losing my place. Of the field. F adjoin S1. Since it is the splitting field of the general polynomial of degree n. So if I can just, I don't think we're really saying much here. Let's give this thing a label. I mean, we're saying a lot of things actually, but if f of x is equal to this, then it's clear from this expression, right, that that's an element of f with S1 through Sn adjoined, right? But then this over here shows that it's clearly split in this field. So that makes, that a Galois extension, right? Make sense? But there's more. He says, if we have any permutation in Sn, and if it acts on the rational functions in x1 through xn by permuting the subscripts, right? He says it's clear that this gives an automorphism of that. And he says identifying the automorphism with this, with this automorphism identifies Sn as a subgroup of aught. So we basically, just like we were doing in the examples I've erased, we can identify the automorphisms, sigma element of the automorphisms of this guy, right? Over, I guess that one, right? Well, he doesn't say anything about fixing this. He just says that an automorphism of that, what it does is it's going to permute the roots 1 through n. So you can, naturally, again, embed that in Sn. That's what I thought. Well, he says here, well, he says that the elementary symmetric functions, S1 through Sn, are fixed under any permutation of their subscripts, which shows that the subfield subfield f adjoining S1 through Sn is contained in the fixed field of Sn. Well, yeah, I'm not sure I follow that either. But the next thing he writes here, I think we're just about out of time, but the kind of punchline here, which I'll write down and try to explain better next time, is what I was kind of expecting. So, I mean, the punchline I was expecting, it's just how the words he spoke to get there, it wasn't what I was expecting, but it's probably just because I'm missing a detail. So what's the degree of this? Well, 1414 says it's less than or equal to n factorial. But, I mean, that's, again, that's, I think, clear from the arguments at the start of today. But, in fact, it's equality here.
Right. Because they're all like,
Yeah. He says it follows we actually have equality in that that f adjoin S1 through Sn is precisely the fixed field of Sn. So actually this whole paragraph is working to prove that the fixed field of, so there's a lot going on here. He's using the labeling correspondence to look at automorphisms in terms of how they're acting on the x1 through xn. And then he's looking at the fixed field of Sn, and he says the fixed field of Sn is this thing. And so since that's the fixed field of Sn, that means that we get equality here. But let's try to work that out carefully next time, yeah? And then, you know, it's not long, all of a sudden he's got these gory formulas for like the quadratics and the Galois group of a quartic, and, you know, and then I think that then leads us into the kind of exciting stuff about solvable and radical extensions, which is where we get much closer to the result that I've been selling, namely that we, you know, show we can't build a general quintic formula. Yep. Anyway, thanks guys.